Section 11.5, we're doing the gas laws, and this law we're going to do the relationship between temperature and pressure. This is credited to Lussac. I think his name's Guy Lussac, a French fellow, and he is forever immortalized as the guy who knows how pressure and temperature works. It's a law, which means no one even bothers them anymore. Everybody thinks it's right. So, pressure and temperature. Have you ever been told that you can't throw a spray can into a fire? What'll happen? Well, there's gas in that spray can. That's why it's a spray can. If you had like a spray paint or even hairspray or anything like that that's a metal can with gas in it, there's a pressure to it. And if you increase the temperature of that gas, then the gas will move around faster and faster and faster. That was the kinetic molecular theory from section 1, if you remember. Well, if it moves faster, it's going to bump into the sides of that container more frequently, more frequently, more frequently. If the pressure exceeds the elastic limit of that steel or whatever that can's made out of, or plastic or anything, it'll explode, right? So the temperature is related to the pressure, in that as the temperature goes up, the pressure will also go up. And that pressure can destroy, and if you have something like a metal can, you end up with shrapnel. You certainly do not want little pieces of metal going at 1,000 miles an hour into your eyes. It would be bad, so don't do it. Okay? So we realize that this is now a direct relationship. As pressure goes up, temperature goes up. As temperature goes up, pressure goes up. So when you do the formula, you're going to have a fraction. So the pressure and the temperature are inverted. So P over T. So P1 over T1 equals P2 over T2. That way, when you figure this out, all you do is figure out what they're asking for. They're going to give you 3 pieces of information. You have the last one. That's the unknown. So solve for it. Put it by itself. Put everything else on the other side. Multiply the tops. Divide by the bottoms. And that's how you do it. So P1 over T1 equals P2 over T2. There's your formula. And whatever you want to solve, you're going to solve. So if you want P2, okay, then you get rid of T2. T2 is on the bottom, so you make it on the top of the other side. So P1 times T2 over T1 gives you P2. Whatever you want to solve, you can. And then you fill in those 3 pieces of information, and the one you're lacking, everything else will cancel properly, and you'll be able to get it. Okay, so just examples. 2 atmospheres, 18 Celsius. What's the new pressure when the temperature is 62 Celsius? Okay, now here's something to keep in mind. It's the Kelvin pressure. You must have the Kelvin pressure to do this. So to turn Celsius into Kelvin, you're going to add 273 degrees. I think it's actually 273.15 if I'm not mistaken, but adding 273 to that 18 and then adding 273 to that 62 will give you these numbers that you see at the bottom, 291, 335. That's where they got them. So it has to be Kelvin degrees to do it, and then you get everything else by itself. That's how you do it. So solve for P2 in this case. Fill in the 3 that you're given, and you'll have the new pressure atmospheres. Use the gas laws to complete with increases, decreases. Pressure when volume decreases. All right, well, this is Boyle's law. As the balloon gets smaller, the air molecules or the gas molecules are going to bump more frequently into the edges, meaning that the pressure goes up. So as volume decreases, pressure increases. What about temperature and volume? Okay, temperature and volume is Charles's law, and that is direct relationship. As temperature increases, volume will increase. So it's a direct relationship. What happens with pressure and volume? Okay, pressure and volume. Pressure and volume are inverse. So as V goes from up from 12 to 24, so it doubles, pressure has to go down by 2, so it halves. Okay, so pressure and volume are inverse. Volume and temperature are direct relationships. So as volume goes up, temperature goes up. So temperature is going from 15 to 45. It will triple, then the volume will have to triple as well. Okay, good. Gas has a pressure of a certain pressure, certain temperature. What's the temperature in Celsius if the pressure increases to 150 or 1.5? Now remember, to do the problem, you have to put them in Kelvin, and then they're asking you to put it back into Celsius at the end. The math works with Kelvin. So first you would take 273, you'd add it to the Celsius, and then you're also going to have to change millimeters of mercury to atmospheres. All right, or atmospheres, it doesn't matter because it'll cancel. The atmospheres and millimeters of mercury have to be the same. You can't have two different units. So if you remember, its conversion is 760 torr at 1 atmosphere. So you're going to have to change those first and then put them together and multiply them out. Okay, so what do? We have to change atmospheres to millimeters of mercury. Okay, or millimeters of mercury to atmospheres. It doesn't matter because they'll cancel out at the end. So when you do this, you end up with 1140 millimeters of mercury. Then you have to change the Celsius to Kelvin by adding 273. Okay, now you're going to end up with a Kelvin answer. When you get the Kelvin answer, because your temperature will be in Kelvin, at the very end they wanted Celsius. So you have to subtract 273 to get Celsius. Okay, they're just trying to be cranky, I guess. All right, so here's T2, here's your 3, fill in your 3. You'll end up with 709 Kelvin, and then at the very end you have to subtract 273 to give you your Celsius answer. Okay, vapor pressure. This is actually pretty cool. I could ask a question of when does something boil? And a lot of people say at a certain temperature, okay, because water boils at 100 degrees Celsius. That's a definition. That's where we get Celsius. Celsius was freezing water is 0, boiling water is 100. Well, that's because at sea level, 100 degrees is boiling water. Because at sea level, the water is trying to expand as it gets hotter, and what will happen is as the molecules are trying to escape into the atmosphere above the pot that it's boiling in, it has to overcome the pressure pushing down. Think of it as an arm wrestling. The air is pushing down with the air pressure. The water is pushing up, trying to go into gas stage, trying to go out as gas. If the air pressure is high, it takes more energy to boil. So if you are lower than sea level, it's going to take more than 100 degrees to boil that water. The water would be higher, and a pressure cooker does that. Pressure cooker will increase the pressure so that the water temperature is higher. Right? But if you were at lower than sea level, it would take more heat to boil that water. It would have to boil at higher than 100. If you're up on a hill where there's low pressure, then there's not as much air to overcome. The pressure is less, and so water boils at a lower temperature. Okay, so on top of a mountain, even on top of your roof, water boils at a lower temperature on your second floor than on your first floor. Okay, so if you're on the roof or on the basement, water would boil at a higher temperature in the basement. Water would boil at a lower temperature on the roof. If you're on a mountain, it would boil even lower. In fact, on the back of the brownie mix, it's going to say high elevation equations because you don't cook the brownies in the oven for as long because it doesn't require as much heat because the pressure is lower. All right, that's pretty cool. So you can really, restaurants that are very high up on mountains, in beautiful mountains, really have to be careful because baking is awful, because they end up overcooking everything, because if you cook it for the same temperature as you would at sea level, it would be tough as a rock. Okay, so what if you had no atmosphere at all? What if you were in space? At space, you don't even need 100 degrees. It would boil at 0. So it's called a triple point. A triple point is where water melts from ice to liquid water at 0, and with no pressure at all, in a vacuum, it would also go straight into vapor and boil, essentially. So you would end up with little bubbles in your water, even though it's not 100 degrees, which is pretty cool, I think. Okay, you can see the bubbles. That's the gas. That is the gas that has escaped, and those bubbles are bursting, and that water vapor is inside the gas, or it is the gas, and it goes into the atmosphere. Okay, so let's look. As the boiling point of water depends on the vapor pressure. So if you have 760, which is sea level, it takes 100 degrees to boil. But if you go lower, higher in the atmosphere, so up a mountain, so it's not so much atmosphere, it doesn't boil as much. It boils at 90. And if you go all the way down to 5 millimeters mercury, which is almost a vacuum, it will boil at the same temperature that it melts. That's why it's called a triple point. It melts from ice into liquid and boils from liquid into gas, all at the same temperature, all at 0. Pretty cool. You never knew that the universe was so cool. Okay. So if you pressurize something, if you make a pressure chamber, then you can increase that temperature of water that it boils at. The temperature of the boiling water would be higher. So if you need it to be hot enough to, say, sterilize surgical equipment, you want to put it in an autoclave, which is a pressure cooker. Essentially, it's a pressure cooker to clean things. All right. So if the atmospheric is 760 and the vapor pressure is 760, okay, then it occurs. It has to overcome. I wonder if that's a trick question. Let's look at the answer. Yeah, it occurs because it's just barely. But if you have more pressure than the vapor pressure, if the atmospheric pressure pushing down is more than the vapor pressure pushing up, it doesn't boil yet. Have you ever heated the water for the spaghetti and it doesn't boil? I mean, it's because you have to have enough pressure to overcome the atmospheric pressure that's pushing down, because it's an arm wrestle. That's what it is. All right. See you in class.